So hello, I am Nir Bachrach, and I'm presenting my work that's called Distributional Robustness from Pricing to Actions. So a bit at the beginning, some backgrounds about second price auctions with reserve price. And there is a seller that wants to sell one item to possibly n bidders. And the seller decides on a reserve price R. Each bidder places a bid, and the winner is the highest bidder as long as the bid is higher than the reserve price. The payment that the bidder will need to pay is simply the maximum between the second highest bid and the reserve price. So this is just a bit of background.
Can we switch you to this so you need to be a little bit louder? This will get you closer.
So,
you can leave the other one on, it's fine, but talking to the...
Okay. So a nice thing about second price auctions with reserve price that they are truthful, and it's something that we are interested in this paper, and we only look on truthful mechanisms. This means that each bidder doesn't benefit from ever placing a bid that is different than its own valuation for the item. And an example for second price auctions is eBay that allows automatic bidding, which basically simulates second price auctions. So about our setting, we have a single item auctions, and we have n independently identical distributed bidders who are drawn for their valuation is drawn from an unknown distribution f. The seller only knows two things about this distribution. They know the expected value mu and an upper bound we call overline v. Our goal is to find a max min for the expected revenue only using second price auctions with randomized reserve price. Okay, so this problem is actually a zero-sum game between a seller that decides on a pricing distribution Q and an adversary that decides on the distribution for the valuations under the constraints the seller known. So the goal is to maximize, the seller's goal is to maximize the expected revenue, and the adversary goal is to minimize it. And since it's now a zero-sum game, we can sell for an equilibrium, and it will solve the max min problem as well. A bit before we present formally our results, we'll show our takeaway. What we find is the second price auctions with randomized reserve price, which are relatively simple mechanisms, are max min optimal mechanisms among all truthful mechanisms. And we don't just find a solution for optimal second price auction, we find the optimal mechanism when there are only two bidders. In the case there are more than two bidders, we also show that it's no longer the case, and we can't find an equilibrium among all mechanisms. And if there is an equilibrium, it will not be a second price auction. Okay. So a bit of what known in similar settings. There is a work of Koresko for single bidder that they show a solution for the price, a distribution for the price. This distribution is presented right here, and it's called the log uniform distribution. And an interesting fact about it, it makes the adversary indifferent among all distribution on the same support. This distribution will also show up in our results, so it's quite important. There's also work from Zutzlatev that doesn't allow randomization of the reserve price, and what he finds is that the seller can't benefit from placing a higher reserve price than any positive reserve price. The max min optimal reserve price would be 0. So there's also work actually in this conference by Chet that doesn't assume identical and independence, and I don't need to say too much. You will see it later. So our main results, we find an equilibrium for this problem. An equilibrium we name Q star and S star. And about the Q star, it has a positive probability to get a reserve price of 0. So there is a positive probability that our mechanism will simply be a second price auction. And the rest of the support will be over an interval where the Poisson distribution will be proportional to exactly the log uniform divided by the worst case evaluations distribution, which we name S star. And additionally, like I mentioned earlier, the second price auction with reserve price is maximum optimal among all truthful mechanisms. So we don't initially look for this solution, but we do find it. And we'll present an example for those distributions. When mu is equal to 0.2, we generate our expected revenue of 0.098. And when we do not allow randomization, the optimal revenue will be 0.04. So we offer an improvement of almost 150%. And this improvement will approach to infinity when either the mean value or the upper bound approaches either 0 or infinity, which basically means that the less knowledge we have about the bidders, the more we can benefit from randomization. Okay, so a bit about this result. The F star we found is actually a truncated equal revenue distribution. And what it means, it generates the same revenue among all undominated truthful mechanisms, which is how we proved that it's a optimal, maximum optimal mechanism among all truthful mechanisms, and not only the second price auctions. And the reason it's an equilibrium, of course, is because using a second price auction, we can force the adversary to choose this equal revenue distribution, and it can't do anything better. So we also provide a bit of intuition about it that will result that we can see how it relates to the case of a single bidder. When we ignore ties that can happen, we can look on a single bidder, on one of the bidders, and see how much this bidder will have to pay in order to get the item, and how much to win the item. And this value, we call the effective price for this bidder, is the maximum between the bid of the other bidder and the reserve price. So this effective price is distributed by a distribution that is simply Q star times F star. And since Q star is proportional to log uniform divided by F star, this effective distribution is proportional to log uniform, which is the same distribution that is true for a single bidder. I would also like to note that this approach does not actually help us to prove these results, because we need to ignore ties, and it's not really the case, but it's helped us to get intuition of what's actually happening. And we also find a solution for when there are more than two bidders, and we find also an equilibrium. However, this time we don't always can benefit from the randomization, and when the ratio between our expected revenue and the upper bound is a bit too high, we find that the best second price auction is simply to not have a reserve price. And when it's, we have a formula for it, when it's too high. Now, if it's not too high, we can benefit from randomization, but we can't force the adversary to use the equal revenue distribution, which is why this is not, it's not an optimal mechanism among all truthful mechanisms. So it's a big difference between the case of two bidders and more than two bidders, where we can force it to be. In the case of two bidders, the worst case distribution of the valuations is the truncated equal revenue distribution, but for more than 2 bidders, it's not longer the case, and the max-min optimal mechanism would be a bit more complicated. So, a bit conclusions. When there are only n bidders, we can benefit from randomization to increase our expected revenue. When there are only 2 bidders, the second price auction is optimal among all true-false mechanisms. And we also establish a difference between the case of 2 bidders and more than 2 bidders, where this simple mechanism of second price auctions with a reserve price is optimal for one, and it's no longer optimal for the latter. However, we also have a bit of open questions, which is we don't know what is actually the max-min optimal mechanism for more than 2 bidders. And we also don't, we think it will be interesting to find how the results holds if we, instead of knowing upper bound, we would know an upper bound on, for example, the second moment or I forgot. And another thing is also we don't know how it's held up in a different benchmark, because we only optimize for max min, but it might be not very good if you want to optimize regret. So that's it. I have a few references, and that we add.
So you have quite a lot of time for questions. Shall we, I would suggest we start in the room and then hand over to Thomas if there's online questions.
Thanks for a very nice talk. A clarification question first. Is it the case that there's a gap between the max-min optimal mechanism and second price auctions, or that your proof technique doesn't work for 3 bidders?
We find an equilibrium for the second price auctions, and for the worst case distribution of the valuations, we also find an example of a mechanism that can benefit a higher expected revenue. So there is a gap. It's not.
Question is, so does that mechanism that you found that does better, does it sometimes serve a bidder that's not the highest bidder? Is that what happens? Because intuitively, it seems to me that if you always do a highest bid wins, that's equivalent to second price reserve in this case, correct?
It's always the highest bidder, but the payment will not always be the maximum between, like, it will not always be the second price or the reserve price. And it's not very hard to find the optimal mechanism in this case, because we can use the marathon and the ironing, and that's it. It's pretty easy to find a gap there.
So you talked a little bit about what happens when you take V over bar and mu off to infinity and 0 respectively. But the one parameter you didn't talk about a lot was the V lower bar, the minimum. What happens in terms of how useful randomization is when that starts to go to 0?
We computed using the mean value and the upper bound. It's simply where the support needs to be for the equal revenue distribution to have the expected revenue we expect. So it's not a parameter we get; it's a parameter we compute using the other ones.
The revenue degrades with your estimate of the mean. Do you know how the revenue degrades with your estimate of the mean? Like if you don't know the mean exactly?
If you don't know the mean exactly, it's the only distribution that can be only a point mass on this mean. So
Can you speak louder?
if only the mean, if the mean value and the upper bound are the same, there is only one distribution that the...
I'm saying that you don't know the mean exactly. You're estimating it from data. If there's an error there, do you lose a lot?
We actually haven't looked into it. We thought about it, but there's a lot of other things we looked at on instead, so I can't answer it.
You mentioned that for more than 2 bidders, you cannot benefit from randomization. So intuitively, what changes from n equal to 2 to n greater than 2? That.
Can you repeat that?
So you mentioned that for more than 2 bidders, you can't benefit from randomization. So intuitively, what changes from 2 bidders to more than 2?
Can benefit from randomization, but not in every case. It depends on the ratio between the mean value and the upper bound. But what happens is that the effect of the reserve price is lower the more bidders you have. So you can only affect the reserve price, and it simply has less effect. So.
Do you want to ask whether there's questions online? No. Try the mic.
Okay. Are there any questions online?
I'm not seeing any questions from Gather so far.
Okay, let's thank Nir again.